Hello, everyone. This is sort of a bonus video that doesn't necessarily connect to anything, although it will have some connections to what I happen to be doing in combinatorics. But it was just a random thing. Someone in my combinatorics class named Dan posted this from Fermat's library, noting that if you happen to take the number 987654321 and divide it by the number 1, 2, 3, 4, 5, 6, 7, 8, 9, then you get this number that is ridiculously close to 8. Okay, in fact, there are 7 zeros there after the 8. And so, of course, I saw this and I needed to know why this is true. And so I wanted to show you today how you can use some various sorts of math that you probably know if you're watching this video in order to see that this is true. So here we go. 4, 3, 2, 1 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So I'm first going to notice that I'm going to write this, of course, as a combination of two numbers. So I'm going to call the numerator n and the denominator d. I'm not being super creative here. But I want to figure out what the numerator is. So, of course, it is 987654321. But if I want to actually write this in a way that's super helpful, well, I'm going to break it up by digit, because the pattern here is something about the digits. It's something about the fact that the digits are increasing by 1 in reverse order. So that's 1 plus, and then this is in the tens place, so that's 2 times 10 plus, and then that's 3 times 10 squared, 4 times 10 cubed, plus dot 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 up to plus 9 times 10 to the 8th. Oops. I can remove that now. Okay, so here is our number. And so that I could write that as the sum as I goes from 1 to 9 of I times 10 to the I minus 1. Okay, I want to take a step back in thinking about this number, and I want to sort of throw the 10 out for the time being. So I want to rewrite this as a function, which is f of x is the sum as I goes from 1 to 9 of I times x to the I minus 1, so that n, we can remember for ourselves, is just f of 10. But I want to look at this function f of x itself, and I want to notice, if you've had some calculus, that every term in this sum is just the derivative of x to the I. Okay. So this weird backwards 987654321 number is somehow slightly secretly coming out of adding a bunch of derivatives of polynomials and then plugging 10 in. Okay. So what I'm saying then is that f of x here, it's the derivative of the sum as I goes from 1 to 9 of x to the I. Now, this has the beauty of being a nice little geometric series that goes x plus x squared plus x cubed plus x to the fourth up to plus x to the ninth. And we have a nice formula for the sum of such a thing. But the formula will look even nicer if I actually start this at 0. Okay. Now, you're 100% right to complain that I can't just go changing things because it will look nicer. But in this case, I can actually get away with doing the thing I just did, because what I did is just instead of making it start with x to the first, I made it start with x to the 0th. But x to the 0th is 1, whose derivative is 0. So all I've done here is just make this something that I know a convenient formula for. Okay. Namely, and by coincidence, we had just actually talked about this in combinatorics. This is the sum of the finite geometric series whose first term is 1 and whose common ratio is x, and which has 10 total terms. So this is the derivative of this. Okay. And so now you get to have the bonus of watching me do a quotient rule problem, because I want to actually write out what that derivative is. Okay. Namely, that derivative is, so it's the derivative of the top times the bottom, so it is 10x to the 9th times x minus 1 minus, and then the numerator times the derivative of the denominator. The derivative of the denominator is just 1, so this is minus x to the 10th plus 1, all divided by, and then by the denominator squared, so by x minus 1 squared. And I'm going to clean that up a little bit. So, namely, that's going to be a 10x to the 10th minus 10x to the 9th minus x to the 10th plus 1 over x minus 1 squared. And I can go ahead and merge those terms. So there will be a 9x to the 10th minus 10x to the 9th plus 1, all divided by x minus 1 squared. Okay, and this, again, is our f of x. And I want to be sure I understand what's happening here is that this is a function that has the property that the numerator of the thing I'm looking for is exactly this function with the number 10 plugged into it. So if you don't believe me, you can pull up Wolfram Alpha and plug 10 into this function, and you'll see you get exactly 987654321. Now, you can debate whether this looks nicer than what we actually had over here, but certainly it's going to make our lives much easier. So that deals with the numerator. Next up, I have to deal with the denominator. And so the denominator is this number, 98765, or sorry, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's the same number, but backwards. Okay. So when I go ahead and write that down, I'm going to write it as a sum. Okay, and so I'm still going to write it as a sum with 9 terms. And so I'm still going to make it I times 10 to the... And then I have to decide what the power that goes with it is. But I think you can decide the power that goes with I is 9 minus I. Okay. So the power of 10, for example, that goes with I equal 9 should be 0 because 9 is the last digit over here. And then it should go with 10 to the first for 8, 10 to the second for 7, all the way up to with 10 to the 8th for 1, because this is 1 times 10 to the 8th for that term. Okay. Now I want to do a little bit of algebra magic here. So namely, I'm going to notice that there is a 10 to the 9th in every one of these terms. So the first thing I did when I sat down to do this by myself was to factor out a 10 to the 9th. But it's going to turn out, for reasons that you'll see very shortly, we actually want to factor out a 10 to the 8th. So I'm going to write this as 10 to the 8th times the sum as I goes from 1 to 9 of I times 10 to the 1 minus I. Okay, and all I did was factor a 10 to the 8th out of every term in this sum and put it at the front. Okay, now why is that helpful? Well, that's helpful because I can rewrite the thing I just did. as being equal to, so this is still the denominator we're talking about here, that is 10 to the 8th times the sum as I goes from 1 to 9 of I times, and now instead of writing this as a 10, I'm going to write it as a 1/10. Okay. Because all these powers are really negative, right? As soon as I is 2 or bigger, this is 10 to some negative power, so I'd rather rewrite it as positive powers of 1/10. So this is namely 1/10 to the I minus 1 power. Okay. And you can take a second to convince yourself that all I really did here was rewrite 10 as 10 to the minus 1 to the minus 1, and then pull one of the minus 1s into the exponent. But in particular, those are definitely different ways of writing the same number. Okay, so now, why on earth was that a good idea? Why did I factor out a 10 to the 8th and not a 10 to the 9th? Because if I'd factored out a 10 to the 9th, then it would just be to the I, and that would look so much nicer. But there's a good reason. And the good reason is that earlier I defined this function f of x to be the sum as I goes from 1 to 9 of I times x to the I minus 1. And so in particular, this piece that we have right now, that's just that function f, but evaluated at x equal 1/10. So this big long string here of equalities that lands at that the denominator here is 10 to the 8th times f of 1/10. That is our denominator. And so the punchline of everything we've done so far is that if you take this number we started with, n over d, and you invent this function f, then you can rewrite this thing as f of 10 divided by 10 to the 8th times f of 1/10. Okay. Now, so far, that's been a giant waste of time because nothing nice at all has happened yet. But nice things are about to happen because remember that f of x, our function that we originally wrote like this, we managed to simplify, or change, if you don't think this is simpler, into this function instead. So I'm going to rewrite my n over d here as this mess with 10 in it. So it is 9 times 10 to the 10th minus 10 times 10 to the 9th plus 1 divided by 10 minus 1 squared. That's n, all divided by, and now 10 to the 8th times, and now f of 1/10, which is going to be 9 times, and I'm going to write this as 10 to the minus 10th, minus 10 times 10 to the minus 9th, plus 1, all divided by 1/10 minus 1 squared. Okay. Now, I'm going to fully acknowledge that definitely doesn't look better. But let's go ahead and simplify this as much as we can. So in particular, I'm definitely going to stop writing this as a fraction over a fraction. I'm going to rewrite this as being the numerator times the reciprocal of the denominator, and I'm going to make all the obvious simplifications that I can. Okay. So let's start again on this thing that was previously the numerator. So that is 9 times 10 to the 10th minus, and then this is now 10 to the 10th because it's 110 times 9 tens multiplied together. That's just the same thing as 10 tens multiplied together, plus 1 divided by, and then this is just 9 squared. 9 squared, I'll just write as 9 squared, although you could write it as 81, whichever makes you happier. Okay, and now I need to remember we're multiplying by the reciprocal of this thing. So the thing that was the numerator here now is going to become the denominator. So it's going to be 10 to the 8th times, okay. And I'm going to notice everything in this numerator is tiny except the 1. So I'm going to put the 1 at front to remind me of that. So this is 1 minus. Okay, and the second smallest thing here is actually this term, which is a 10 to the minus 8th. And then plus 9 times 10 to the minus 10th. Okay, and then the numerator up here is now 1/10 minus 1 squared, which, because it's squared, is the same as 1 minus 1/10 squared. So this is 9 squared divided by 10 squared. Okay, in particular, if you look at everything that's happening, these 9 squareds are going to cancel. This 10 squared is going to go join that 10 to the 8th in the denominator here, so that'll become a 10 to the 10th times, okay, and so the denominator here will be 10 to the 10th times 1 minus 10 to the minus 8th plus 9 times 10 to the minus 10th. Okay. And the numerator here, now we have a 9 times 10 to the 10th minus a 10 to the 10th. That's an 8 times 10 to the 10th plus 1. Okay, and now if you remember, the thing we're trying to get to is this. You'll notice there's an 8 in it. And so after all of this work, we have gotten to the point where this is our 8. That's the 8 that we're looking for. Okay, so I want to make that 8 really pop out. So to do that, I'm going to divide both the numerator and denominator here by 10 to the 10th. Okay. And so after I divide both the numerator and denominator by 10 to the 10th, here's what I'm going to have. Namely, I'm going to have 8 times, and so then I'm going to have 8 times 1 plus, and I actually also need to factor an 8 out of this, so this is 1 over 8 times 10 to the 10th. All divided by, and then, well, there already was a 10 to the 10th factored out, 1 minus 10 to the minus 8th plus 9 times 10 to the minus 2nd. Okay. Now, what I want you to notice here is how close the numerator and denominator of this fraction are to 0. Or sorry, are to 1. Because this number, this is an 1/8 of 10 to the minus 10th. So this number, if I were to write it out in the numerator, this is going to be 8 times. And the 1/8 only makes it smaller, so this is something like 1.000000000. So that's 9 zeros. There's actually then, because of the 8th, a 1 more 0, and then a 125, if you think about what 1/8 is in decimal. Okay. So the numerator here is ridiculously close to 1. Likewise, if I work out the denominator here, it's 1, but then minus, and now... Oh, I'm sorry, I miscopied this. This 10 to the minus 2, it's a 10 to the minus 10th. I just miscopied it from line to line. So this denominator here, I am subtracting from this a 10 to the minus 8th, which is a 0.000000001, and then I am adding to it a 9 times 10 to the minus 10th, which is a 0.000000. Let's see, and so 1, 2, 3, 1, 2, 3, 1, 2, 3, 9. Okay. And so in particular, this number is super, super, super close to 1 again. So if I were to write out this denominator here, it would end up looking like this. It would end up looking like 8 times. And so there is one more 0 here, right? 1, 2, 3, 4, 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So if I were to line this up properly, this 1 would end up here. So I end up subtracting a total of point a bunch of zeros 9, 1. And so how many zeros is it? It's 1, 2, 3, 4, 5, 6, 7 zeros. So that means my denominator here is 0.9999919. Okay. And my numerator here is 1 point, and then that same thing. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 5. Okay. Like that. Okay. So this number that we calculated, we have now shown is this. Okay. But this number, we know, is absurdly, absurdly close to being exactly 1. And in fact, you can even tell it's slightly bigger than 1, like if it were to be anything. But it's slightly, slightly larger than 1, which again explains why it's not exactly 8. It's 8, a bunch of zeros, 7 zeros in fact, followed by, and then a little bit of a decimal. Okay. I'm going to wrap up there for this video and trust that you believe that this number is absurdly close to 1, and so hence you see why this number is absurdly close to 8. I will note 2 things that you can do on your own if you want to think more about this. So one of them is you can think about, how do I know how close this number is to 1? Could I, without a calculator, prove that this number is within, say, 10 to the minus 7th of 1? And hint, you can by considering how this number relates to the power series of 1 over 1 minus x. Okay. Namely, it is the power series of 1 over 1 minus x with a tiny, tiny, tiny value plugged in for x to make this the denominator. And then multiplied by this number, which is 1 plus some tiny, tiny, tiny number. Okay. So that's extension 1. Extension 2 is you can think about, okay, this seemed like a huge fluke at first when you wrote this down. You wrote down this 9876 blah, 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 divided by this other thing. And so the very first thing I tried when I looked at this and was setting down to try and figure out why on earth this could possibly be true, was I tried to say, okay, what if instead of taking 987654321 and dividing it by 1, 2, 3, 4, 5, 6, 7, 8, 9, what if I took just 54321 divided by 1, 2, 3, 4, 5? And as it happens, that doesn't work out to be nice at all. It works out to be just some basically ugly decimal. So it turns out that something special here happened. that relates to the fact that we're in base 10. And in fact, if you look through the proof I just gave and rewatch every step, you can find the step where it magically happened that we used sort of all the digits base 10 and things ended up working out nicely. Something canceled that otherwise wouldn't have. And that's what made this be close to an integer. But the other thing you can do if you want to extend this is you can think, okay, well, we happen to use base 10 for no other reason than we were born with 10 fingers. And so what if instead we had been born with 12 fingers and would use base 12, or maybe you're a computer science person and you like thinking in hexadecimal, and so you could imagine, like, what would this look like in hexadecimal? And so you could go back through and you can try and alter this argument just slightly and figure out, okay, do analogous things hold in other bases, or is this some unique special property of base 10? All right, I'm going to leave off there for now. But until next time, be well.